In our last video, we were introduced to the trig graphs, and we looked at what we call the parent graph in each case. So y equals sine x, and we said sine starts at the center. Y equals cos x, so that's a very similar shape to the sine graph, but cos starts at 1. And then y equals tan x. Tan has got two asymptotes at x equals 90 and x equals 270. But we can work out other values of tan. We could work out the 45 in between here, the 135, the 225, and the 315. Okay, and in order to draw any graph, we could literally plot it point by point by working out a certain number of degrees. Okay, so the parent graph is in each case like this. Sine, cos, and tan, I've made no changes. But in this graph, we're going to start learning how to transform these graphs, and they are going to start shifting around and stretching up and down. So let's have a look at what changes we can expect to see. So next to each parent graph, I have now put the standard equation form. Okay, so you'll see y equals a sine x plus q, a cos x plus q, a tan x plus q. And these a and q values are going to tell us something very important about the graph. So in each instance, if I multiply by a, this is going to be what we call a vertical stretch. Okay, meaning that I'm going to multiply, okay, or squash. Sometimes we use a small number there and then our graph actually becomes smaller. But we multiply each y value by whatever this a coordinate or a value is. We'll have a look at some practical examples, and I think it'll make so much sense. Okay, but a vertical stretch or squash affects what we call, or what the proper terminology is, the amplitude of a graph. Okay, so sine and cos have amplitudes. Tan graph doesn't have an amplitude, remember, because it relies on the maximum and the minimum. So that's why we refer to a vertical stretch or squash, because it's not always as clear-cut as an amplitude. All right, so that's the a value. That's going to stretch out our graph. And then the q value in each case is actually going to result in a shift. So a vertical shift. We're going to shift the graph up or down. All right, so now what we've got is our parent graphs, but we can start to stretch them out and we can start to move them up and down. Let's have a look at some examples, because I think that's when it really starts to sink in. Okay, so here we are asked to sketch the following graphs on the same system of axes for theta between 0 and 360. So that's all perfect. We've got y equals sine, 2 sine x. Okay, so that's going to stretch it. That's the amplitude there. Sine x plus 2, that's going to shift it. And then minus 2 sine x minus 2, that's going to be an interesting one to see. Okay, but I always find it so helpful to draw when I have a parent graph to look at. So what I've done here is just very lightly in yellow, I've put our parent graph in there. The sine graph starts at center, at 90 it's at 1, at 180 it's at 0, 270 and minus 1, 360 and 0. And now I can show you nice and clearly how we adapt these. So let's color code. We're going to do this first one in blue. Okay, y is equal to 2 sine x. So I'm going to take every point, every y value on my parent graph, and multiply it by 2. Okay, so 0, that's where it is here. 0 times 2 is 0. Then at 90, we are sitting on 1, and 1 times 2 is 2. At 180, 0, that's our y value there. 0 times 2 is 0. At 270, we're sitting at minus 1. Minus 1 times 2 is minus 2. And at 360, again, 0. And so 0 times 2 is 0. So here we have it. We are adapting our parent graph. And look how nicely this shows us what the stretch actually looks at. So the amplitude here, an amplitude of a sine graph is normally 1, the distance between rest and the highest point. Now it's going to be 2. So that's the graph of y equals 2 sine x, a vertical stretch. Okay, the second graph here, let's color code that to be this red color. Okay, y equals sine x plus 2. In this instance, I'm not going to be multiplying by 2 like I was there. I'm just going to be adding 2 to each of these parent graph points. Okay, so I'm going to start again at 0. 0 plus 2 takes me up to 2. Plot my point. Then here at 90 and 1, 1 plus 2 takes me up to 3. I'm going to plot the point. And I'm going to carry on. 0 plus 2 minus 1 plus 2. 0 plus 2. So there I've got all of my points now plotted, and I can draw the new graph. Okay, so there we have it. Y equals sine x plus 2. It's a little bit of a bumpy one because I couldn't see the other side of my hand. Y equals sine x plus 2. So what's happened in our first graph is the amplitude has changed. Okay, let's make a note for ourselves. This was an amplitude change. In the second graph, if you look at it, you'll see the amplitude hasn't changed. My rest point has actually shifted. And so the distance between rest and the highest point is still 1 unit. But this case, it shifted, and it was a vertical shift. It moved up 2 places. Okay, what happens now when I start to combine everything? Ooh, minus 2 sine x minus 2. Okay, well, I'm just going to do it one step at a time. So let's color code again. Let's call this one this greenish color. I'm going to take each point. I'm going to multiply it by minus 2, and then I'm going to hop 2 places down. Okay, so 0 times minus 2 is 0. And then we hop 1, 2. So my new point is going to be there at minus 2. Okay, next up, 90 and 1. 1 times minus 2 is minus 2. And then we're going to hop 1, 2 places down. That's going to go all the way down there to minus 4. Okay. 180 and 0 we've already seen. Times by minus 2 is just 0. Hop it down 2 places there. Then, where are we? 270 and minus 1. Minus 1 times minus 2, that's now positive 2. Ooh, that's there. And then hop down 1, 2 places. So that's now going to be there on the axis. Okay, and then 360 and 0 is going to do what all the other zeros did. So let's draw that graph. There we have the graph of y equals minus 2 sine x minus 2. Okay, so what happened here? We've got an amplitude change. The amplitude now is going to be 2. But the minus did something very interesting. So instead of our graph going up first and increasing slope, it's decreased. And so what that minus did, okay, we also had this vertical shift, which, we've been seeing. So that vertical shift happened. But this minus here meant that it was a reflection of the parent graph. Okay, so fascinating things. But if you know this parent graph well, you'll be able to answer your questions with a lot of understanding. So you can, grade 10s, you can plot these graphs by substituting in the x values that you see on your axes. So you could say minus 2 on your calculator, sine of 0. Minus 2, and it'll give you this point. Minus 2 sine of 90 minus 2, and it'll give you that point. You can point by point plot it, but I do find it so helpful to answer from understanding. So you can see the parent graph, and you can adapt and say, am I stretching it? Am I shifting it? Am I reflecting it, stretching it, and shifting it? Let's have a look at 2 more examples here of sketches. So y is equal to a half cos x plus 1, and y is equal to minus tan x minus 1. So let's get those parent graphs in place. Okay, it looks quite busy, but that's not a problem. We can make sense of the 2. Okay, a half cos x plus 1 means that this thing is now, it's not actually going to stretch, it's going to squash. So here where it was at 1, it's going to go to a half, and then it's going to move up 1 place. Let's color code again so we don't get confused. For the cos graph, I'm going to take each point, so that's here. Let's just make sure we can see it. Okay, I'm going to take each point, and I'm going to multiply by a half and then add 1. So each y coordinates. Okay, 1 times a half is a half plus 1 takes me there. 0 times a half doesn't matter, stays at 0. Plus 1 takes me up to there. Okay, 180 and minus 1. Minus 1 times a half is minus a half. Plus 1 takes me up to there. 270, that's another 0, so it's going to do the same thing that happened at 90. And 360 is at 1, it's going to do the same thing that happened at 0. So there we have y is equal to a half cos x plus 1. So in each case, multiply and add all of those points. And again, you can point by point plot on your calculator. But have a look what happened here. The amplitude now is so small. It's just a half distance between the maximum and rest. Or remember, another way of working out amplitude was to take the maximum. So in this case, the maximum now is 1.5 minus the minimum, which is just a half, and divide that by 2. And you'll see that gives us a little amplitude there of a half. Okay, squashed, and then we shifted it up 1. Now let's look at the tan graph. We want to reflect it. That's what the minus is saying. And then we want to move it down 1 unit. Okay, I'm just making this a little bit more visible for us. Okay, so tan, remember we can't do the 90 and the 270 because of the asymptotes, so those stay in place. But we can do the other points. So 0 doesn't help to reflect 0, but then we can minus 1. 45 and 1 is the other point we work with. Hey? So we're going to reflect that, and then we're going to minus 1. So if we reflect it, it'll end up here, but then we need to minus 1. Okay, so that takes us there. So there's our first arm. Okay, then we can take this 135 and we can reflect it and minus 1. It's going to end up there on the axis. 0, we don't really reflect, but we can minus 1. And then what are we dealing with here? This one is here at 1. We reflect it and we minus 1. So we can end up down there. Okay, so this tan graph now, it's like its whole center has moved down there to minus 1. Okay, and then finally the last little arm, we take that one there, 315, we reflect it and we minus 1. Let's do that. So that takes us there to on our axis. And then 360, that's a 0. 0 reflected is still 0, and then we minus 1. So that's going to end up over there. And so this is going to be this way around. Okay, so that's the graph. Y equals minus tan x minus 1. See, so as long as you know that a number in front multiplying by the graph is going to affect the amplitude or sometimes reflect the graph, and a number after that, the Q value, is going to shift it up and down, you can actually draw these graphs with a very logical approach. Now let's really test your understanding. These graphs have been drawn for us. So f of x equals a sine x plus q, and g of x equals b cos x plus p are sketched below. Okay, sine graph, cos graph there. I can spot the difference. Let's quickly color code them. So sine graph, that one goes up and down. Cos graph, that one goes there. Okay, that I can already see as an upside down cos graph, because straight away my mind is thinking of parent graphs where the cos graph starts at 1 and then it goes downhill and then only back up. Cos is like a little smiley face. Okay, now they say write down the amplitude and range of f and g. Okay, so f is this yellow one, g is this blue one. Okay, let's answer in yellow and in blue. So f, the range, y is an element. Okay, then we just need to list the smallest number and the biggest number. So from minus 3 up to 1, minus 3 up to 1. Okay, that's our range. And then amplitude, we can actually use this now, the max and the minimum. We can say it's maximum, so that's 1 minus the minimum divided by 2. Okay, 1 minus 3, that's the same as 1 plus 3. So 4 over 2, which is going to give us an answer of 2. Okay, and then amplitude and range of G. So G, Y is an element. We start with the smallest. please remember to go from smallest to biggest so you don't lose marks. Minus 1 up to 1. So we're going to write that down. Okay, and then I can tell you that the amplitude is, and you can find the place of rest and then see, but this formula is helpful. So it's maximum 1 minus minimum over 2. Okay, that becomes 1 plus 1, so 2 over 2. The amplitude there is 1. Okay, and now they want us to determine the values of A, Q, B, and P. In other words, what is the equation here? Okay, so the sine graph is going the right way, up and then down. Okay, we can see that the amplitude is 2, so I can already say, well, then that y is equal to 2 sine x. I always look at what's happening here. Sine x, and then does it actually go to 2? Because that sine starts at the center and then goes up to 2, down to 0. But it's not. Do you see that instead of starting at 0, it's starting at minus 1? So that means it's shifted down one place. Okay, and now that I know that, I can say, well, therefore A is equal to 2 and Q is equal to minus 1. Okay, and then for our cos graph, remember what I said, cos is normally a smiley face. So this is a reflection because it's a sad face now. So that's going to definitely be a minus, but the amplitude is 1. So I can say minus 1 cos x, or just minus cos x. And then, let's see, cos normally starts at 1. It's now starting at minus 1, which is a perfect reflection there. So it looks to me like it hasn't shifted at all. The center line is still here on the x-axis. So I'm going to say then that's plus 0, right? It hasn't shifted at all. It's just an upside down graph. So that means, therefore, B is equal to minus 1 and P is equal to 0. And so there you have it. You can look at a graph, and if you understand amplitude and shifts, then you can work out the equation of that graph.